right? Okay, so that concludes the first part of my talk. Next, I'm going to go to the security part of the talk. So any questions about the first part? Okay. So I think I have about 9 minutes and 30 seconds, and I'm going to just tell you a little bit about the issues and the challenges in this area. As I said, this is a brand new area for me too. We just started this late last year, so I don't have a lot of hard results. Okay. But I will tell you an approach that we're going to take based on knowledge or rule-based systems. So let's see. Okay, motivations. These are embedded systems. Your future car may not have a steering wheel, so joysticks. Okay. Patient monitoring in hospital. So this is the space shuttle. So typically in this system, security is becoming important, but typically people are more concerned with getting the correct result and having it verified for timing correctness and logical correctness. And security is not the main topic there. But I think the more these systems are deployed, I think it's that we need to incorporate a certain level of a security mechanism. So I do work also in embedded systems. So this is an Intel board that we have to check out some DVS algorithms that we have developed to basically save power while still meeting the timing constraint. This is a simple fixed wireless sensor network testbed that my student and another colleague in the department have set up. And we have an intrusion detection system running here. And this is really a test bed because one of my students has a sleeping bag underneath. Okay, so yeah. So he's not underneath right now, but there are lots of wiring and power stuff downstairs. He's in the table here. And afterwards he took it out. He said, "That's okay. I show this. It's more funny. It's a test bed, and there's really a bed underneath. Okay, it's sleeping bag. What we are doing right now is we want to specify this IDS in real-time logic. Okay, so that's one project, and then use the tool to analyze. So here, of course, we're focused on the timing. So from the time an intruder goes in and modify things, or maybe send an incorrect package, we like to bound this response time in detection. So that's one problem. Okay, with respect to this setup. Okay. Now, a typical real-time system is like this. So you have a system that is being monitored and controlled. Okay, that's T. And the sensor input. And then there's a decision system consisting of hardware and software. State information tells you about what's happening before. And then you have to make a decision to determine what to do next. It could be changing the temperature setting. So you activate the air conditioner. Or it could be opening a valve to let fluids go through let's say, in a refinery or a chemical process. Or it could be activating an anti-lock brake, right, to avoid skidding. So all of this can be modeled like this. But in reality, there are more in modern control systems. Okay, so you have a user interface. The UI folks, user interface folks would be working on this. There's networking. So you may have this system in a control area network, or you may have a system that is actually activated remotely, maybe through an internet. That would not be good, unless you certify and verify that you have the system safely operating. So you don't want to have a robot arm in another room in Houston, and I'm changing it here, and hacker gets in and modify this transmission. So. Or you have something maybe more closely coupled, like in a car. And then within the control system, you have monitoring, decision-making, actuation, and also the target system, so which is shown in this simplified picture. Okay, so what are the issues in an IDS in such a setting? Some of this, of course, in the wireless sensor networks, the nodes may be running on battery. So the the first thing, of course, is accuracy. That's well known to you, right? So it should IDS should identify null or few false positives, null or few false negatives. But here, timeliness is important. So you don't want to add the IDS and violate the original timing constraint of the application. Okay, so if your sensor is going to detect maybe temperature changes or maybe CO2 in the air, then I don't want to affect that timing. If you add this IDS module to it. Scalability. Can you scale from small to large or vice versa? And power awareness. This is something that has not been thought of much in the security community, and we intend to work on this. How do you get some security, some intrusion detection, without basically violating the real-time constraints that you have? Okay, so one approach we are taking is based on automatic rule-based generation. So I think here there's a group that is working on automata inlining, so you can model the legal and illegal behavior. Because if you want to model everything, that's not possible. If you want to trace all the possible packets being exchanged, all the execution, all the library calls, that's not possible. But here we give another twist. And the reason is I work on rule-based systems for a long time. And we have a polynomial time tool that can tell you whether a system can meet the deadline constraint. So meaning the worst case execution time, it's always less than or equal to the deadline. And we can do this for, a large class of systems. Again, the problem is not decidable in general. So the objective here is to automatically generate this rule-based program that represent the legal execution behavior of a given application program in this embedded system. And now, but the tool that I have only tells you the timing. Here we are checking for security. So we need to encode this as timing, basically timing constraint. And we have some experience doing that, but not encoding security, but rather regular safety properties. So we conjecture that we can do this. And our technique to do the analysis fast is using something called semantic analysis. That's why we can avoid the state space, the reachability graph analysis that is needed if you use an automata-based technique. Okay. Now, at runtime, we're going to append new rules to this automatically generated rule set that has the legal behavior represented. And this uses a new program. Now, if these rules are dependent on the current execution sequences, if some of them are becoming illegal or maybe it's from the intruder, then we'll be able to detect it with this technique. Again, this is incremental, so it's more efficient. I think I need to skip an example because I have a minute and a half left. But anyway, this is the form of the rule base. It's a propositional logic-based language. We also have a first-order logic-based language for MRL. EQL is the simple one. But this is enough for our purpose. And we use semantic analysis and based on special forms that we have proven to satisfy certain timing constraint. Okay, so we can have a program like this and analyze using this strategy. Again, using a compositional and incremental approach. So we can analyze a rule-based program, breaking it down into smaller pieces and then combining the results. Okay, so I just want to conclude the talk. There's a lot of avenues for further research in this area, and I'll be happy to share with you the some of the workshop papers where I have described more details. They are available on my website. And I like to, of course, show you some pictures. Photography is my hobby, so I usually take pictures of my group at conferences. And this is at RTAS 2005. Stefan is here from NUS. This is at the Martian Robot Competition at RTSS. Okay. This is at my lab. There's a CS open house. This is Wayne Wu from Princeton visiting us. Jeanette Wynn, who is now the head of CISE.